And now, friends, what is a science communication ceremony without any science communication? It would be a scandal, and that's why I want you all to give it up for Nobel Laureate in Physiology or Medicine, May-Britt Moser, and the Trondheim Soloists.
It's about space, it's about the brain, it's about memory. When I was a child, I was curious, and you heard about curiosity today. And I was so curious about what happens inside us when we think about things, when we learn, and when we do things. So now we've been out in space, and I'm just wondering whether you would like to join me from space and into the brain, deep into the brain. Would you like that? Yeah. Good. So, sorry, I just get the mouse here, just a second. There it is. Yes. So the brain consists of billions and billions of nerve cells, and these cells, they are activated by small electrical signals. And then they talk to each other by sending small chemicals signals over this tiny gap that is called a synapse, so that the neighbor cell will be also electrically activated. And do you know what? it's possible to put small microphones into the brain and listen to these small electrical signals. We can magnify them, say, 10,000 times, and then we can listen to them. And the popcorn sound of a single brain cells. Another thing that I need to tell you is that there is a brain structure just here behind our ears, on both sides of our head, that is called not the seahorse, but the hippocampus in Latin. And you see why? Because here to the left, you see the hippocampus, how it looks like in our brain. And then, of course, it was very similar to a seahorse. So that is why it's called the hippocampus. When you leave this room, and if you don't remember the hippocampus, you might wonder whether your hippocampus is working. Because the hippocampus, you need that to encode new facta information about facts and also about events. This information was known already in the 50s because patients that had lesions in this structure, they couldn't remember new things and they couldn't find their way. And that led one of my supervisors, John O'Keefe, to go into this structure with these small sensors, with these microphones, and he tried to listen to one single cell at a time, and his big question, that was, why is this cell active? And why does it stop being active? And he was sitting there observing the rat when the rat was running around in a box chasing chocolate. And he was searching, and he was listening to this popcorn sound of the cell in the hippocampus of the rat. I want to invite you now to our lab, Edvard Moser's and my lab, here in Trondheim, so that you can listen and figure out for yourself what is this cell responding to. So you will hear one single hippocampal cell being active. And there are some small red dots showing where the cell is active. And the rat that you see here, I'm allowed to call Oscar. So let's run the movie. So here's Oscar just searching for chocolate. And it's not so that there's more chocolate in that corner, because chocolate is sprinkled around in the whole environment. And there's another thing that I want you to see here, and that is that Oscar is a happy rat. If he's not happy, I have had rats my home as a pet, then he wouldn't like to move and play like Oscar is doing. To the right here, you see a way to show the activity of these cells. So blue indicates no activity, and warm colors, that's a lot of activity. If you record say 100 of such cells at the same time, you will see that the different cells will be active at different parts of the environment. In addition, you can predict the position of the animal with an error of only 5 centimeters if you record activity for, say, 10, 20 minutes. Isn't that amazing? You can predict the position of the rat by just looking which cells are active and where. So you know, we have a lot of visitors at our center, and we also have the staff working there. And we got a new staff, a senior advisor, Tor Grunbeck, who came there, and I had to show him the lab. And I said to him, "Do you hear this popcorn sound? In my head," and I'm not a musician, it's like music. Do you agree? And he's also a musician. And he said, "Yes. And you know what? I know a composer." And the composer, is he allowed to come to your lab? And I said, "Yes, bring the composer to the lab." And the composer, he had a colleague who was a movie maker. So the composer, Bertil Parma Johansen, and the video maker, Johan Magnus Elvemo, came to the lab. And they got recordings from our cells. And in all presentations, in scientific presentations, you have to tell the method. Now I'm going to show you a video of how Bertil transcribed these signals that he got when he begged me, "Can I please get some of these signals, the cells signals, with me home so that I can use it and make music?" And he got cell recordings from Richard Gardner in our lab. And this is the method that he used. And he also got help from another person in our lab, Vadim Floro. So again, the rat is running around in the box. So, as I said, Edward Moser and I, we were so lucky that we were trained by John O'Keefe, who we shared the Nobel Prize with in 2014. And we came back here to Trondheim and started our lab from scratch. But we had these burning questions with us, and we really wanted to understand, how can these cells be so specific, so having this spatial bias? Where does it come from? And I want to tell you briefly about some experiments that we did in order to address that question. So here you see a rodent brain. It's in fact a rabbit brain, but it looks very similar to a rat brain. This is the olfactory bulb, this is the cerebellum, you have the spinal cord down here, you have the cortex, and then you have this beautiful sausage that is the hippocampus in the rat. So you see it looks a tiny bit different from the beautiful seahorse that we bring with us. If you cut this sausage in two, you can look into the different cells that talk to each other. And this place cell that John O'Keefe discovered, that was found here in Cornu ammonis 1, the sheep horn. And my other supervisor, Per Andersen, suggested that the information is going through a trisynaptic loop. Here from entorhinal cortex to dentate to C3 and up to C1. So it is like a loop in a computer program. And we asked, is it so that this information has to go through this loop in order to produce this beautiful place cell pattern? We addressed that question by having great students in our lab who could cut this connection between the rest of the hippocampus and the CR1. So then this pathway is cut, and surprisingly, we still saw these place cells. That means that this information does not need to go through this loop. Either it's generated in the C1 itself, or it's coming from outside. As you heard the musician said, people had been there before. So people had been in the entorhinal cortex before and concluded that there's not much spatial information there. But those of you who attended Edward's talk earlier this morning, he said, don't listen to what people tell you. Do what you believe in. We did that. So we went into the structure entorhinal cortex together with students in the lab, Marianne Fyn and Sturla Molden, and also guided by Menno Witter, who was a professor in Holland at that time. We wanted to explore the entorhinal cortex of the rat to see if there are some spatial signals in this brain structure. Here you see a rat brain from behind. The cerebellum is removed. You see this beautiful colored area that is entorhinal cortex, the part of the cortex that is around the rhinal fissure. This part of the brain is giving information to the hippocampus. So we decided to put our small microphones very dorsal because we knew that this portion of the entorhinal cortex is sending information to the hippocampus, where John O'Keefe found these place cells. And you know, when we put our small sensors into this structure, we could read in scientific journals afterwards that people were shocked by the pattern that we discovered. Look. This is the path of the animal, the black traces. So the animal is doing as we saw on the video, searching for chocolate. One blue dot, that is the tiny electrical signal emitted from this cell in entorhinal cortex. But what is special about this activity compared to the cell that you just learned about, the place cell? Do you see what's special? Isn't it extremely regular, this pattern? Should we check? You can fit in equilateral triangles into a pattern that is made by biology, made by a brain cell. Isn't this amazing? And you see, you can just tile your bathroom with this beautiful pattern, or your kitchen if you prefer. But I asked you if you would like to join me in a journey deep into the brain. This is as deep as you can come into the brain. So this area doesn't have access to eyes or to ears or to odors directly. So how can this cell fire so precisely if it doesn't have this kind of information? This pattern can be made by self-motion information. So when the animal is moving back and forth, maybe there are some cells in the brain of the rat that is recording the speed of the animal and the direction. How many of you think that that is the case? I wouldn't have told you if it's not the case. So we can go to the first cell. In fact, this cell was discovered earlier than we tried to check whether it was in the entorhinal cortex, in another structure in a dorsal presubiculum by Jim Rank and Taube afterwards. But this is a special cell, and now we're going to play. I'm going to demonstrate how this cell works. So you see this mouse? When the mouse is going here to west, this is the firing activity, and you see that it's only firing whenever the animal is going to west. Or another example, if the animal is going to northwest, then the cell is firing. So say that we record such a cell from me, and this head direction cell, Øyvind, will fire whenever I go in that direction. Okay? Okay. Thank you. Then there is another cell. We can call it either a Flintstone cell, a speed cell, or a speedometer. So this was also discovered in our lab by, this time, Emilio Kropf. And should we demonstrate the speed cell before I explain the figure? What do you think? Okay. Are you ready? You record? Okay. So what Øyvind and I tried to demonstrate here is what you see on this plot. So this animal has a car. It's a very environmentally friendly car because the animal has to do like Flintstone did, run. And the computer is deciding the speed of this car. The car is driving up and down, north and south. And every time the animal is driving north, we change the speed here in the midway, here, halfway. And you see that the speed is in gray, and the activity, the number of these small electrical signals are counted here, so that is the firing rate of the cell. And you see that the firing rate of the cell follows the speed of the animal perfectly. So when the animal is driving north, you see there are a lot of activity. When you slow the car, then there is almost no activity. And you see the same thing when the animal is going south. You have low activity of this cell when the animal is driving very slow, and then when the animal is driving really fast, then this cell is very, very active. So why is this useful? Because if we give this information, and that is very plausible because these cells are surrounding the grid cells that we discovered, these cells. So they can then tell this cell the direction of the animal and the speed of the animal. So then it doesn't matter whether the animal is stopping and eating chocolate or turning or whatever it's doing. The cell can be precise. Then you can wonder, we have worked now with rats. Do we have such cells? We started first to check this in mice in our lab. And we found then, together with Marianne Fyn, that these mice, they have grid cells. Then there is a fantastic lab in Israel, led by Nahum Ulanovsky, and he found these cells in the bat. And the bat and the rat, they are far away on the phylogenetic tree, so they are not relatives. Then Beth Buffalo, she showed such cells in the monkey. When the monkey was watching a screen, then she could find activity in these cells when the animal moved its eyes. And finally, these are my daughters, so we haven't checked them, but we assume that they have such a good spatial navigation ability, so we assume they have grid cells, but it has been shown in epileptic patients where they go in with these small microphones and check where the focus of the epileptic seizure is, using the same techniques that we use for our rats. They have shown that humans, we also have grid cells. You might ask, why is it interesting to study these grid cells relating to play cells? Is it so that these grid cells that we discovered, are they the ones that are important to create these play cells in the hippocampus? I have to tell you one more information from our lab, from Turkel Hafting. And that is, this is a section of the brain. It's a sagittal section. That means it's going this direction. You see the beautiful hippocampus here. You see this colorful area here, which is the entorhinal cortex. And what is so interesting here is that at the top of this structure, entorhinal cortex, you see the small-scaled grids. And then they expand, so the resolution of this grid cell is getting worse and worse when you go deeper and deeper into the brain. But that is useful, because if you want to go from these grid cells to the place cell, you can imagine that you just collapse them, you align them, like we've tried here with the different scales of grid cells. You align them, and then you see that the signals in the middle will add up, and at the ends here, it will cancel each other out. So you end up with one bump, and that is the bump that we saw in the hippocampus. What you've also heard is that these structures are important not only for spatial navigation, but for creating our memories. Now I want to bring you to the west coast of Norway and share some of the deepest memories West Coasters have. I'm sorry, it's difficult for me to speak because this is so emotional for me. This beautiful video from my home, and then this beautiful music, and the singer from my home, from Ekspenes, from Herøy, where I'm from. So thank you so much. So, you know, emotions, they will keep information in your brain. But sometimes we have to remember things that is not so emotional. And then space is very useful as a retrieval cue for memory. And I can show you a drawing made by my daughter, Eileen Moser, and I asked her if she could just think of how she would remember the different countries in South America if she used a memory palace. So you see the different countries here in South America that she wanted to name here, and then you have the memory palace. She was thinking that for remembering Chile, Chile wallpaper could be useful. So when you come into the kitchen, you see a wall decorated with chili. Then you can move into the next room, and you meet this angry Tina. Then you can move up here to see Bolivar, the dog. And here there's a photo of my supervisor, Per Andersen. And you can see that you can make your own drawings in your mind to remember, to make some cues so that you remember both the names of these countries, but also where they are and which country they are neighboring. So this is an ancient memory technique. So what I would like to do now is to ask, if we have such a memory palace in our brains, how are these rooms coming about that we start to know now? We have the place cells, we have the grid cells, we have the speed cells, we have the head direction cells, we have the spatial system, we have the house, we have the rooms. But we need to fill our rooms with something. And before we go to the cells that are useful for filling our memory palace, I want to show you how the artists try to describe the memory palace for you. So you saw all the memories in the different rooms. But did you see what happened at the end of the movie? There was a floodlight going into the different rooms, and there was nothing. The rooms were empty. And you know, this happens when cells are dying in the structure of the hippocampus or the entorhinal cortex. You lose the cells, you lose the memory, and you lose the spatial navigation. In our lab, we have a PhD student who was doing a special technique that is called patch clamp. You suck the cell, and sometimes you can hold the signal that is coming from this tiny cell for some while, and you hear pop, 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 pop. But then, since you suck the cell, sometimes it might explode. And you know what? The composer, he heard about this, and he said, "Wow, can I get these sounds from you, Øyvind?" And so it's not this Øyvind, Øyvind Høydal in our lab. And he said, "Yes, of course, take it." And Bertil made music of it. So this is, I'm sure, the first time you've ever heard a classic orchestra playing a dying cell. Do you know what? If We all have, of course, memory problems. But if you start to get a bit more memory problems than normal, maybe it's wise to go to the scanner. It has been shown that people coming to the doctor and complaining about memory problems, if they do a brain scan and the entorhinal cortex, where we discovered the grid cells, if that is shrunken, if it's much smaller than it should be normally, then there is a high possibility that you might, at a later stage, develop Alzheimer's disease. So the entorhinal cortex and these grid cells and other cells are important for both your memory and for spatial navigation. So in the last part of my talk, I would like to tell you a tiny bit of more cells that we find in the entorhinal cortex. And of course, if they die, you lose that information. So this is the hippocampus, and the entorhinal cortex is sending information to the hippocampus about events, objects, odors, and space. So space in the medial entorhinal cortex, and then all these other memory items are typically in the lateral entorhinal cortex. So I'm going to demonstrate some of these cells for you. One cell was discovered in another lab, in Jim Knyrim's lab, and he decided to call it an object cell. So he was finding toys, and he was just giving toys to the animal, putting it into the box, toys like this, and then he just did like John O'Keefe did and asked, are these cells responding to these objects or not? And you see the white dots here, and you see the warm colors surrounding the cells around the objects. That means that these cells respond to the objects. What happens if you remove the objects? Those cells were discovered in our lab by Albert Sau. So he trained animals in the box with Lego Duplo towers that he built, and the animal knew that this tower should be in this position. Every day the rat came and visited the environment. Maybe it was Oscar again. So when Oscar was here, and then he came one day, and the tower was gone. But there are cells in Oscar's brain that will fire where the object had been. And Albert thought this was so interesting. And scientists, I'm sorry, we are like children. We are so curious that we just have to play and address question after questions to get answers. So Albert moved the object, and he made a new trace. And he moved the object again, and he got a new trace. And in this way, he got trace after trace in the environment. So we decided to call these cells tracers. So they keep the memory of where the object is in the room. Now, I hope that there are nobody who could tell about this to the journals, because we haven't published this cell. There are some embargo problems, you know. So Øyvind Højdal was so kind that he gave me this slide and Øyvind Højdal is a PhD student at my lab. And he also played with towers. But what he discovered is that when the animal is close to this toy or the tower, The cell will always be active at one side of the object. And it doesn't matter whether the animal is looking at the object, touching the object, if the object is hanging, it will always be active towards that direction. So that is why we decided to call it an object vector cells. So yesterday I had an agreement with Anders. Are you willing to be my object today too? So then I'm going to demonstrate an object vector cell for you. My object, Anders Larsen, and Øyvind, you play the popcorn sound, and so my field will be here, okay? And you can just be my object, stand there. Okay. Thank you to both. So now you know what the object vector cell is. And that's quite useful for language. You have to know where objects are in relation to yourself. Is it above you? Is it at the right side, left side, in front, or back? So we are starting to fill our memory palace with quite interesting cells. Don't you agree? Good. You know, how many of you have been at the Viking Museum in York? No? Yeah! Do you remember that there was something special about the museum in York? The smell! Yes, exactly. And you know, they sell the Viking smells. So I know a scientist, Professor John Aggleton in Cardiff, and he told me about, he had bought Viking odors, and they were not good. So he had bought Viking odors, and he presented these Viking odors to people that he knew had been in the Museum of York. And they hadn't been there for 20, 30 years. And when they smelled the odor, they said, Vikings! It must be the museum in York. So the odor is an extremely potent retrieval cue. Do we get odor information to our hippocampus? Yes, we do. And I'm going to demonstrate that with the rat Emma. So Emma, she has a task where we present either chocolate odor or banana odors. And she has to learn that if the chocolate is presented when she's sniffing here, she has to go there. If she is smelling banana, she has to go to the right corner. Do you think she can do it? Of course, Emma is excellent. But she is doing some errors, so please be careful when you watch the movie where Emma is performing her best. Chocolate. Chocolate. Banana. Yeah. Chocolate. Emma, chocolate. Too late. Now she's frustrated. Poor Emma. I want to get out of this. Banana. Oh, yeah. She just needed to concentrate. Banana. Chocolate. And you know, we can put our small microphones or sensors into the brain of Emma, into the entorhinal cortex and into the hippocampus. And that was Kei Igarashi, a postdoc in the lab, who could then show how the entorhinal cortex interacted with hippocampus and made odor maps in the two structures. And the lateral entorhinal cortex was the teacher of the hippocampus and taught the hippocampus about the space and the odor. So that means we have the spatial system that is fed into the hippocampus, making the frames of the memory palace. We have a lot of cells signaling odors, where they are associated to objects, and so on. And as I said, when cells are dying, that will empty the rooms in the memory palace. In the next and the last movie that I'm going to show, that's a recording of the composer's grandmother from the West Coast, and it's a recording from 1958, when the grandmother was playing the organ that Edvard Moser's dad had built in Haramsøya. And you will listen to her beautiful voice, and the composer and the movie maker have used her music to illustrate what happens when the rooms in the memory palace get empty. So please follow me on this movie. Sally, and all the rest of the orchestra. We are so proud of them here in Trondheim and in the rest of the world.